We're here in Boulder at NEON, which is the National Ecological Observatory Network, with Torey Ploeger. Torey studied aerospace engineering, and she works here as a systems verification engineer. So Torey, thank you so much for being here. Can you start us off with telling us about your path to becoming an engineer?
Sure. Well, at the end of high school, I had a really great physics teacher, Mr. Miles, and he inspired me to believe that I could become a physics teacher and that I could lead the next generation and have a positive impact on them and inspire them to solve the problems of the world. This is all very idealistic. I took a much more practical approach to my idea, though, and decided to pursue engineering as a means of getting out of college quickly and maybe doing something with myself before having to get a doctorate, which is kind of what you had to do in physics at that time to make much of yourself. So I decided to pursue engineering, in particular aerospace, because it was more specialized and would offer me potentially more marketability.
And then what was your first job out of college? You just got your aerospace engineering degree. Where did you go from there?
I went to a company called Rocketdyne. A lot of people recognize the name Rocketdyne because they made the space shuttle main engines. They make engines for the Delta IV and the Delta I and all those kind of famous vehicles. I was working on the J2X, doing testing for the J2X upper stage engine for the Space Launch System, which is NASA's sort of next generation of the space shuttle.
And now you're a systems verification engineer, which sounds really different than an aerospace engineer. So how does that work?
So I guess the misleading thing is that verification is something that's transferable between different industries. It mainly focuses on testing and making sure everything fits together at a higher level. So that's basically what I was doing with the J2X program, even though it was with rocket engines, which are totally different from ecology. It was still taking requirements, taking our expectations, and making sure that the end product fit those. So similarly, when I was looking for a job and found out about NEON, I saw that they had a need for people who could take requirements, take expectations, and make sure that the system fit.
Can you tell us a little bit more about what NEON does, the National Ecological Observatory Network?
Sure. So NEON is fully funded by the National Science Foundation, and it's a project with a mission to create a continental scale ecological data set. And the whole purpose of this data set is to help us understand the impact that humans have on the environment so we can work on reducing that impact. It's not just sensor oriented. I think a lot of the things that we've talked about so far indicate, it's all about the sensors. It's all about temperature and wind speed and these nifty things we can mount on a tower and then just collect data from. It's also very human-based. We have an observational component where we send people into the field to capture and release species, and they record their observations. We send people up in aerial observatory platforms, so we actually outfit planes with some of our sensors, and people go up and do observations from there.
One of the things we wanted to ask you is, what is this really cool thing that's sitting on the table in front of us?
This is a grape. We plug our sensors into these. They're part of our data acquisition system. So this is sort of the first stop for all the data that comes from our sensors, all of our subsystems, of which there are approximately 90. But each subsystem is made to adapt to one of the ports in this grape. The data comes in, the data comes in these serial ports, and it comes out of this Ethernet cable. It's all converted to digital data, and then it's sent to one of many Ethernet switches on our towers, our aquatic sites, and that data is then, all condensed and sent in packets back to headquarters to be filtered and then analyzed.
And it's collected outside. This lives outside somewhere?
Yeah, this actually, strangely, I know it doesn't look it, is designed to withstand environmental anomalies, such as rain.
Anomalous as it is.
Yeah, it actually hangs upside down on what we call arbors, hence the name grape. And actually, we have really funny names for them. So we have Concord grapes, which are 24 volt, a little bit heavy duty. Merlot grapes, not quite as heavy, 12 volt. We have Zinfandel grapes, which, like Zinfandel wine, don't have the big outer shell. They go inside of boxes to protect them. But generally, like grapes, they hang on arbors like this. And they're protected by like this gigantic, like Darth Vader-esque helmet that protects them from, downwelling moisture and radiation and all those things. And then in addition, all of these little caps we put on here are actually sealed on the inside. So once you cover one of these ports when it's not in use with a cap, it's weatherproof.
And you have sensors on land, in water, and in the air.
And in the air.
And you're sensing what kinds of things?
Well, goes from humidity, basic standard weather station type things, humidity, temperature, wind speed, to more complex systems that measure air quality, what percentage of the air is one gas versus another. We have systems that measure the salinity of water, the conductivity of water, the pH of water in our groundwater wells and streams and rivers.
And to measure all these things, you must have a pretty diverse set of expertise on staff. What kind of people work here?
I'd say that the diversity really is found in our science department, because you have to have people who are experts on aquatics, and then, well, are they experts on aquatic minerals, aquatic species, how the water interacts with the atmosphere? We've got like that level of resolution on all of our scientists. For terrestrial systems, we have experts on atmosphere. We have experts on land-based species. We have, I'd say that our strength is really in our scientists. And then on the engineering side, you have your pretty standard gamut of mechanical engineers, electrical engineers, systems engineers, designers, drafters, logistics. It's full scale, considering how recently we formed.
And do the engineers interact with scientists very much?
They try not to, but it's my job to make them. That's if at all possible, they really avoid it. But yes, we actually, the way we organize is usually around subsystems. And on one subsystem, you'll have an integrated product team. And on that integrated product team, you'll have, say, an electrical engineer, mechanical engineer, systems engineer, a scientist, the scientist who knows the most about that particular sensor system. And they all work together to bring this system to production.
And what type of problems do you solve here at NEON?
The complicated kind.
The best kind.
Yeah. So, as I said, it's all about how it fits together. You might have a mechanical engineer, an electrical engineer, and a scientist come up with a subsystem, say radiation system.
So that's something that detects radiation.
It detects radiation, and we measure that in like watts per square meter. How bright the sun is. If there's overcast sky, then you'll get a different level of radiation. If you're in the forest, you'll get a different level of radiation versus if you're in the desert. And that particular subsystem maybe has its mounting hardware, has the package that is that subsystem has to connect into the rest of the world. It has to connect to headquarters. We have to be able to get data from it. So my job as a verification engineer is to make sure that that radiation system has the power that it needs, that it fits into our power budget, to make sure that if it needs any heating or cooling, if it needs any extra stuff, that it has it. It's my job to make sure that our manufacturing processes can provide the components. It's my job to make sure that it fits into the big picture and that it functions.
So we like to think about engineering as a helping profession. What people do you help?
Well, I guess this is one of my favorite questions. It kind of fits into my ideology as a person, the way I like to think that I view the world. I'm helping the next generation, because all this data that we're going to collect once we're done with 5-year construction will be collected over the next 30 years. And it's really going to help arm the next generation with what they need to make sure that we take care of this planet. The continental scale of what we're doing is really going to paint a much broader picture and a much more comprehensive picture than we've ever had in the past.
How do you use what you learned in college as an aerospace engineering student in your current role as a systems verification engineer?
I actually keep all my textbooks from college right on my desk.
Too.
Yeah, you'd be surprised how often they come in really handy. Don't lose those. Don't lose those. I would say, college, at least undergrad, is really about developing that framework of knowledge, and you use that framework as a tool, and you can manipulate it, to accomplish whatever ends you seek. So, I'm not an electrical engineer, but I did the power budget for NEON, the whole observatory. I'm not an electrical engineer, but I used what I learned in classes like Mechatronics to figure out how all that fits together. I'm not a thermodynamics expert, but I put together the heating and cooling budget for all of our enclosed spaces that are HVAC controlled. Once again, textbooks came in really handy for that, but understanding even where to start came from my education.
What about your current job didn't yet exist when you were an engineering student?
You know, I'd say for the most part, surprisingly, what we do at NEON doesn't involve very much new technology. All the components were there before, but the concept of putting them all together was the biggest idea. That said, there is one particular sort of pet project of a scientist here. He's sorted out an algorithm to convert aerial imaging of hydrogen. So you just fly a plane over a forest and you can use spectroscopy to figure out how much hydrogen is being emitted by the leaves.
Wow.
And then go and correlate that with our data on the ground about radiation. And you can figure out how factors like wind speed and air quality impact the rate of photosynthesis in the leaves.
Torey, how do you use math in your job?
I typically use math for test results, for sorting out algorithms for models that I want to use to predict, say, a power budget or heating and cooling budget. It's more on the level of algebra and geometry. We don't use so much higher math for the level of modeling that I do. That said, my background in higher math really helps me to understand what I'm taking on. It helps me to understand where to start and what to expect when I'm using certain simpler equations. But once you get into the workplace, I'd say it's more common that you take shortcuts and you simplify, and also that you do a lot of testing to come up with much simpler versions of the complex equations you might have used in college.
What is the coolest thing you get to do in your job?
Climb towers.
Nice.
Yeah, it's a really rather glamorous departure from the cubicle life. I guess most people wouldn't call it glamorous to wear a safety harness and a helmet.
I would.
But right? And sometimes we do exercises here. We'll do safety exercises, or we'll install hardware, prototype hardware on our prototype tower.
Here in Boulder?
Yes, actually right out back. I can show you after this.
Cool.
But we'll go to do that, and we'll put on all our gear, and people look at us the way, you know, the average American looks at an astronaut. So we're all geared up and looking like we're off to fight a battle or something. So it's kind of cool. Lots of hands-on work and lots of glamour.
So I imagine your work requires collaboration with lots of people who have different expertise. Can you give us some examples of people that you collaborate with?
Oh yeah, actually I can give you the most dramatic example, which is the role that systems engineering plays in bridging the divide between science and engineering. I think in college, you know, scientists and engineers are kind of lucky in that they get to work separately and don't have to deal with each other. Oftentimes, you know, in a perfect world, you'd be able to test your science in a vacuum chamber with, you know,
Standard temperature and pressure.
spherically shaped, you know, objects of uniform density. But that's not how things are in the real world. You know, try telling a mechanical engineer that, well, we need to build a 180-foot tower in the forest to measure what's going on in the forest, but it can't impact the forest in any way. And that's, you know, sort of trying to bridge that gap is where most of my interdepartmental communications come in handy.
Now we'd like to talk more generally about your thoughts on engineering and being an engineering professional. Can you tell us about a time in your education or in your career when you weren't successful or maybe failed at something? And then what did you learn from that, if anything?
This is a very interesting question. I'm not trying to be facetious, but the answer is no. And I consider that something I need to work on. I grew up a very perfectionist person who had an extreme fear of failure. And even now, I would say that I tend to take on lower risk projects, lower visibility projects. As an engineer, as a human being, really, that tends to stunt your growth. You know, no great engineer was ever made by hiding in the corner and not taking on high risk activities. And that's something I've actually been working on. And luckily, my manager has been great enough to work with me on that. I think that the best advice I can give from this point in my career is make as many mistakes as you can in college, because the younger you are, the easier they are to fix. You know, go out and do something you really care about and try really hard and fail gallantly and learn how to get back up again and be a success. You don't want to wait until you're, mid-career like I am to have to learn how to do that, because it's really scary. You've got a lot more on the table. You've got your family, and you've got other priorities.
Torey, what was your favorite experience as an engineering student?
Mechatronics, which is...
What is Mechatronics?
Oh, it's only the best class. Mechatronics is where you go into a lab and you have all these theories that you've learned in different courses. And oftentimes they're sort of cross-disciplinary theories, and you have to put them to the test and prove them and sort of develop your engineering intuition. I love Mechatronics for that reason. It was a very scary course for most people. The vast majority of people really hated it. There's a lot of report writing. But what I really loved about it was that it gave me the opportunity to really develop my own opinions about what all that theory means. Because like I said, you can't just test things in a perfect vacuum with objects of uniform density, but how those theories really apply to the real world. And I could develop my intuition and test it, come up with my own tests. It was sort of almost like a self-guided tour of what engineering really means. And I feel like I came out of it realizing I want to be a test engineer. I think that's where I decided I'm going to do this. I really like verification and testing. And it's also where I started to sort of like being an engineer just for being an engineer, not just as a means to becoming a physics teacher.
What do you wish someone would have told you when you were in college?
There are a lot of males in engineering, not so many females. There are a lot of minority students and women who feel intimidated by that. And I feel as if the most important thing that I had to learn on my own, because no one told me, was that it's okay to just be who I am. We're really lucky to be living in a time when a lot of the old ways that things were done, a lot of the old assumptions and presumptions and structure are falling, and we get to be a part of that. And I think it's been way more fulfilling for me in my career that I've been able to say, no, I'm not going to pretend to be one of the guys just to work on a team of all guys. Or no, I'm not going to straighten my hair just to get a job. I'm not going to do any of that. I'm going to do it my way, and it's really paid off. So I'd really encourage you, learn and be smart and, do the things you need to do to be a good engineer, but don't sacrifice who you are for that, because it's never worth it.
Great. Well, is there anything else you want to share with us?
No, I really appreciate getting to do this and getting to speak to your class. It's been a pleasure. And I wish you all best of luck.
You'll see the students around in Boulder, and hopefully you will see Torey around in Boulder and you'll recognize her.
Don't wave, I won't.
Thank you so much for your time.
Of course.